In the previous video, I reviewed my gravitational acceleration measurement and found that my guessed value of 20.85 meters per second squared was wrong, and it's actually more likely to be 20.4 meters per second squared. In that same video, I didn't really touch upon the terminal velocity, so in this one, I will now review my initial guess that the terminal velocity was 35.7 meters per second. Hello, Count Sacke here, back with another Genshin Impact video. Okay, I have to make a confession. I messed up my terminal velocity measurement quite badly, so I shall make up for my mistakes by recalculating and verifying the terminal velocity. This is the third video in a series focused on accurately measuring the gravitational acceleration and terminal velocity. Technically it's the fourth if you count this one, but whatever. If you haven't seen the previous video, there are some statistics concepts I will be using in this video, which I explain there. The main one is the R-squared coefficient. If that doesn't sound familiar for you, well, I would recommend you watch the previous video. I will show the equations like needed for the video, but I won't be explaining the concepts again. With that, let's get started. Aside from the gravitational acceleration being wrong, there also was another issue that I failed to catch, and it's quite jarring. Looking back at the first video, the whole reason why I started reviewing and recalculating everything was because of this part. Based on the equations obtained from the differential equations, the player would technically never hit the terminal velocity. Instead, they just approach it as time ticks on forever and ever. However, this isn't the case in-game. Yup, I literally said it in my video, on script, and somehow I didn't catch my own mistake. I measured the terminal velocity using an equation that doesn't even match what you would expect to see in-game. The equation shown on screen was derived using force analysis on a falling mass experiencing the drag force. Based on this equation, it would take an infinite amount of time to reach the terminal velocity. But, as we observe in Genshin, the player does seem to hit the terminal velocity relatively quickly. Not too fast, but you can definitely observe it if you fall for long enough. I did have one comment by Primary4075 in the last video critiquing my use of the linear kinematic equations to measure gravity. And that person asked, why didn't I curve fit an exponential function to the data points? That's a good question, and it actually made me doubt myself despite my revelation. So I tried fitting the equation to the data from the previous video and got this. It can be seen that based on the R-squared value, the exponential model is actually more accurate at modeling the data. Perhaps the exponential model is truly how we should describe the falling behavior of the player. Hold up, there's something to note here. The difference is very small. A 0.02% better accuracy is very negligible in the grand scheme of things. For now, I think it's best if we check both of them and see in the end which is the more likely model. There's just one thing that we need to consider. If the kinematic equations can't model the terminal velocity, then the answer here should be obvious. So the first question we need to answer is this: can you model the terminal velocity in the kinematic equations? The short answer is yes. The basic idea is that you have two different types of motions. You model these two motions with different equations and voila! You have the terminal velocity from the kinematic equations. This is actually how you'd treat any classical physics problem with multiple types of accelerations and velocities. In the first type of motion, the player is accelerating downwards towards the ground. This means that we have the following equations for this motion. Delta y is equal to gt squared divided by 2 plus vy naught times t. Then delta v is equal to gt, and lastly, v y1 squared minus vy0 squared is equal to 2 times g times delta y. These are just the kinematic equations, and for our case, we only need to consider the first two. For the constant velocity segment of the motion, the acceleration is 0 and we are left with this equation for the change in height. Delta y is equal to v max times t. For us to calculate the total height fallen, we can make use of the general distance formula that I derived in my measuring distances video. I unfortunately didn't have the time to explain how to do the integration back then. This time, I want to provide some idea of how you would do it. Integration is basically a type of addition meant to include continuous changing values. Geometrically, it calculates the area under a curve. This geometrical perspective is very useful but can be quite limited. For what we're doing, we don't really need to go any more in depth than that. When we look at our distance equation, we have velocity multiplied with differential time. If you want to know more about differentials, I talk about them in more depth in my Using Calculus to Solve for Optimal Artifacts video, so check it out if you're interested. This tells us that we need to consider a velocity versus time plot to calculate the integral. The quote-unquote area that we're considering is the velocity multiplies times time. Well, what's velocity times time? That's actually distance. How do I know that? If you consider the units of velocity, it's distance divided by time. And well, distance divided by time multiplied by time, that's just distance. So again, the area under a velocity versus time graph is distance. Let's draw out our plot. I'll indicate the terminal velocity to be at this height. When the object is dropped, the velocity magnitude increases linearly, which is given by this equation. Delta v is equal to g times t. This is just the kinematic equation. We can see that the highest exponent for t is 1, so it plots a straight line. However, once this line reaches the terminal velocity, we should expect that the velocity magnitude will no longer change. This means that our velocity magnitude becomes a horizontal line. This is given by this equation. Vy is equal to Vmax, or just delta V is equal to 0. It doesn't matter what value time is, the velocity remains the same, so we end up with a completely horizontal line. I go into more detail about velocity versus time graphs in this video, so take a look at it if you're interested. To calculate the total height fallen after reaching the terminal velocity, let the total time spent falling be capital T, and the time taken to reach the terminal velocity be Tm. I would like for you to try and figure out how exactly you would calculate the integral. Just remember, for integrals, they geometrically compute the area under a curve, so pause the video and give it a try. You might realize that we can split up the area under this line into two areas, one right triangle and one rectangle. We know the equations for the area of a right triangle and a rectangle, so all we need to do is add them up. The area of a right triangle is 1/2 base times height. The base is the Tm and the height is Vmax. Then for the rectangle, the height is Vmax and then the width is T minus Tm. The total height fallen is now a piecewise graph with two possible motions, depending on how long the player has been falling. If the player has only been falling for a short period of time, so less than Tm seconds or however long it is, the total height fallen is equal to 1/2 g times t squared. However, if the player has been falling for a longer amount of time and has reached the terminal velocity, the height equation becomes Vmax times the quantity T minus Tm divided by 2. Great, so we now have a way to model both the gravitational acceleration and the terminal velocity that the player experiences using the kinematic equations. The thing about this equation is this: we need to know both the value for the terminal velocity and the time it takes to reach the terminal velocity in order for the constant velocity portion to work. The problem is, I'm not sure if we can trust my previously measured terminal velocity, so we also don't know what Tm could be. Ideally, if we can express Vmax and Tm in terms of the gravitational acceleration and height alone, we could make use of our previously measured data and recalculate new values for them. At first, it might look impossible to get anywhere with what we have, but remember, there are quite a few equations at our disposal. If we recall, one of the kinematic equations is the following: delta V equals G times delta T. This implies that Vmax is equal to G times Tm. By definition, we stated that Tm is literally the time it takes for the player to reach the terminal velocity, assuming there is zero initial velocity, or the initial velocity is equal to 0 meters per second. With these two equations, we can actually derive an equation to solve for Tm, in terms of the gravitational acceleration and height. The first thing we need to do is to substitute for Vmax. Next, after some distribution, it can be seen that we're left with a quadratic equation. Tm squared minus 2 times capital T times Tm plus 2h divided by g is equal to 0. When we have a quadratic equation, guess what? We can make use of the quadratic formula. How many of you actually remember that thing? Well, I do. Anyway, after a bunch of simplification, we get this equation for Tm. Now here's a problem. We actually have two possible values for Tm. Obviously, we can only have one, so which of the two is correct? For this, we have to use a bit of logic. Recall that the height equation is only valid in scenarios where the time taken to reach the ground is greater than Tm. The only way this condition would be satisfied is if we choose the one with the minus sign. Think about it, the square root term should be a real positive number for Tm to make any sense. So obviously, t plus any positive number is going to be larger than t. But if Tm equals t plus a constant, this means that Tm would be larger than t. This violates our condition that capital T must be greater than Tm. Therefore, the one with the minus sign is the correct equation. Tm is equal to capital T minus the square root of capital T squared minus 2h divided by g. You can run through the logic again with this one and see that it must be the right one. T minus a real positive number must be less than t. From here, we can calculate the terminal velocity by substituting the value for Tm into the other equation. Vmax is equal to g times Tm. From this previous video, I measured the terminal velocity by falling off a ledge near the top of the Sumeru tree. Luckily, this data has exactly what I need to calculate Tm. All we need to do is change the formulas. We technically no longer need to determine the coefficient k, but I'll calculate it anyway just to be able to compare. In summary, these are the new calculated values. The coefficient k had an average of 0.684, whereas the terminal velocity had an average of about 29.811. Lastly, the time taken to reach the terminal velocity was approximately 1.461 seconds. And here's a comparison with the old values. We can see now that the terminal velocity has decreased by quite a significant margin. For me, I can't help but notice how close the new terminal velocity is to 30 meters per second. I feel like this is actually likely to be hard-coded into the game as it's pretty clean. Trust me, you're not going to be putting 29.81135618 into your program. No, you're just going to put simply like 29.8 maybe at most. maybe 29.81 at most. You don't really go more than 2 or 3 sig figures when you're manually inputting these values. If we take the gravitational acceleration and terminal velocity to be truly equal to 20.4 meters per second squared and 30 meters per second respectively, this would mean that Tm is equal to 30 meters per second divided by 20.4 meters per second squared, which is equal to 1.471 seconds. We can also calculate the minimum height needed to fall in order to reach the terminal velocity with this equation. Hm, which will be the height fallen after a duration of Tm, is equal to Vm squared divided by 2g, and that is equal to 22.059 meters. We currently do have a height versus time graph for 0 to 30 meters in increments of 0.5 meters. While we could focus the analysis on purely the heights greater than 22 meters, we don't have much data. If we include the 166 meter height from Sumeru, we have this huge gap between the 30 meter and 166 meter height, which is quite concerning as we have no idea if anything different happens between those two heights. Based on this, I've decided to collect more data. I specifically wanted to fill the gap between 166 meters, so I just went to a few places, 6 to be exact, measured the heights, and the time taken to fall from said heights. For the methodology behind measuring heights, you can watch my video about measuring distances to measure the time taken to fall the height. I explain this in more detail with my first video on gravity, so be sure to check those out if you're interested. So we currently have 2 different models, one based on kinematics and one based on the drag force. I think it's worth mentioning why we're using these 2 specific models and not anything else. The truth is, we could come up with many different possible models that could try to fit the data. The way we rule out a bunch of these models is by measuring their accuracy, establishing boundary conditions, and for whatever is left, we can make use of Occam's razor. For our case, we measure accuracy with the r-squared term. The closer r-squared is to 1, the more accurate it is, so higher r-squared values are more preferred. But of course, we can see that between our kinematic and drag force model, they both have high r-squared values, so it's not too easy to rule out one or the other just on this alone. The boundary conditions that we have is that at 0 seconds, the height fallen should be 0 meters, and that the velocity should also be 0 meters per second. Both the kinematic and drag force models satisfy these conditions as is shown on screen right now. While this decreases the scope, there are still a lot of possible equations. For instance, I could very easily obtain a more accurate equation and satisfy the boundary conditions by adding more terms into the drag force model. Here are some examples. By all means, it could potentially give us an even greater r-squared, but the thing is, we now have more parameters to consider. What exactly are these C1s and C2s that we just put here? They seem arbitrarily added. Ideally, we want to have the minimum number of independent constants needed to fully compute the equation. The other 2 equations I show have very high r-squared values, but they both have 4 constants. These additional parameters give higher accuracy, but they also mean that they need more tuning to match the experimental results. Overfitting, in layman's terms, basically says that a model tries too hard to make sure that it can predict the sample data accurately. While this might sound good, the thing is, a model is supposed to predict things also outside of your sample data. You want it to predict things you haven't seen before. For example, let's say I measured something at 2 seconds. What happens at 4 seconds? If it only matches things that are within 2 seconds, then that's not really very useful. The model is overfitted to things below 2 seconds. but when I want to see what's at 4 seconds and the model is like, it doesn't match at all, then it's overfitted. One such way a model can try too hard to predict sample data is by adding more constants. And this is why too many constants can be a bit problematic. If you have too few constants, you also have problems. Overfitting can cause a model to easily fail when new data is acquired. In short, an overfitted model is only good at predicting the data. The last reason why I'm only considering these two models is because they're derivable directly from physics. The kinematic model is from the kinematic equations, which assumes that the net force acting on an object is constant. The drag force model includes the drag force, which impedes the object based on its speed. I was literally able to derive an exact equation from the kinematic equations and from the drag force model. They gave me equations that I can use, and I can literally measure the gravitational acceleration directly. I can tell what it is. With these other models where I just added arbitrary constants, I don't know how to measure the gravitational constant. With that, I think it's about time I mention which model I believe to be most likely true. I personally believe that the kinematic model is the correct one. But why? Outside of the extremely high accuracy, it's very simple. From a programming perspective, the kinematic equations are very simple and effective at giving the player movement. They also aren't too computationally expensive as well. Compare that with the drag force model equation. It has an exponential function, which is more computationally expensive. In general, it just makes more sense to use the kinematic equations. Now, computationally expensive doesn't necessarily mean that they wouldn't use it. Some people like to choose things for certain stylistic choices, and the drag force can be an interesting addition to player movement. But for Genshin, I don't think it really is used. In addition, I debate with myself if the kinematic model truly has 2 or 3 constants. We know that Tm is equal to Vmax divided by g. If you can express Tm in terms of the other 2 variables, is it really an independent constant? I'm not sure, but I decided to include it because you need to know Tm in the first place to calculate the height. I also don't have to fine-tune the values for g and Vmax so much to obtain the accuracy that it does. The values that I'm using for the drag force model is using the best possible parameters it can, and it still isn't able to beat the kinematic model in terms of accuracy. For the nail in the coffin, I showed that the drag force model had a larger r-squared value for heights ranging from 0 to 30 meters tall earlier in this video. After I added the heights beyond 30 meters and adjusted the constant coefficients to fit the new data, the r-squared value for the drag force model decreased to 98.63% compared to the kinematic model's 99.78%. This graph here shows what happened to the drag force model after including the heights beyond 30 meters. And well, you can see here that it's actually not really predicting it as well as the kinematic version, which is indicated as linear. In trying to accurately fit the coefficients to the data beyond 30 meters, the model's predictions began to drift away from the heights below 30 meters. The kinematic model has extremely high accuracy, fits the boundary conditions, and doesn't have that many coefficients. What more can you ask? In conclusion, I remeasured the terminal velocity and found it to be about 30 meters per second, as opposed to the initial guess of 35.7 meters per second. I also determined that the most likely correct model for the falling movement in Genshin Impact is given by the kinematic equations rather than the drag force. While I think my values are pretty conclusive, there's always more room for improvement. One can always do more measurements, specifically testing at taller heights, and, well, gathering more times per each fall. With that, this should be the last video about Genshin Impact's gravity and terminal velocity, at least for a while. I don't really have anything else more to add to this one. Well, I already measured things and I got more accurate values, and I think these ones are actually truly correct this time. So yeah, thanks for watching and hope you've enjoyed.